Let's say that I have a die and a coin, and they're both fair. So I have a fair die and a fair coin. And so I'm going to conduct some experiments and look at some events. So we'll pick out a couple of events. Say that event A is that I roll a 6, and event B is that the coin shows heads. Okay, so I have those two events. Now, we know from very basic probability theory that the probability of event A is 1 over 6, and the probability of event B is a half. Right? Given that the die is a fair die and the coin is a fair coin, then we're dealing with sample spaces where the outcomes are all equally likely, so we can easily work out the probabilities. Right. Now, let's talk about conditional probabilities here. So I have two events, so I can look at the conditional probabilities. What's the probability of rolling a 6 given that I flip a head? Well, the coin doesn't have any effect on the die, so the fact that I got a head when I flipped the coin doesn't make any difference to what happens with the die. So really the probability of rolling a 6 should be 1/6 regardless of whether I have a head or a tail. So if I have a head, the probability of rolling a 6 on the die is still 1/6. So it's the same as without the condition. Well, okay, we can turn things around and we can ask for the probability of flipping a head given that the die rolls a 6. Well, again, the die doesn't affect the coin, so that should be the same as without the condition. Right, so you see this relation here between the conditional probabilities and the ordinary probabilities without any conditions. They're the same. Now, just to contrast this situation with another situation, let's pick another event, and I'll pick an event concerning the die roll. Let's say that event C is rolling a number that's at least 4. Okay, so rolling a 4, 5, or 6. So again, we know that the probability of C is 1/2. Okay, because there are 3 successful outcomes there and a total of 6 equally likely outcomes. So we get 3 over 6, which is a half. Now let's look at conditional probabilities. So what's the probability of rolling a 6 given that I roll at least 4? So the probability of A given C. Well, now I only have 3 outcomes to consider, right? 4, 5, or 6, and the probability of one of those 3 is going to be 1 over 3. They're all equally likely. So you see now the probability of A given C is not the same as the probability of A. The probability of A is 1/6, but the probability of A given C is 1/3. And intuitively that makes sense. You can see that, you know, rolling something at least 4 is not going to be unrelated or independent of rolling a 6. What about the other way around? What about the probability of C given A? Well, I'll just do this one for fun. So what's the probability of rolling at least a 4 given that we roll a 6? Well, let's think about that. If we roll a 6, then we have definitely rolled something that's at least 4, so that probability is 1. And again, of course, that's different from the probability of C, which was a half. So what's going on here? Well, when we just look at event A and event B, the conditions don't change the probabilities. On the other hand, if we look at event A and event C, then the conditional probabilities are different from the unconditioned probabilities. So it's clear what's happening here is that, well, the coin flip and the die roll have nothing to do with each other. They're independent. In the language of probability, we say that these are independent trials. And the events A and B are independent events, whereas A and C are dependent or not independent. Okay, and these examples here really capture the essence of what independence means in the context of probability. So let's write down a general definition and see what we can do with that. So in general, if we have two events A and B, we say that they're independent. Let me underline that word there. If the conditional probability of B given A, so the probability of B given A, is the same as the probability of B. In other words, whether or not A happens does not affect the likelihood of B. And the probability of A given B is equal to the probability of A. In other words, whether or not B happens does not affect the likelihood of A. So that's one way to say what independence means. But actually this is not the most common way, and what I'm going to do now is I'm going to take this definition and use it to arrive at the more common way of expressing independence. And the way we're going to do that, of course, is that we know something about these conditional probabilities. So let's recall the multiplication rule. Right? Remember the multiplication law. So the multiplication law for probability said what? It said that the probability of A and B is what? It's the probability of B given A times the probability of A. But now if A and B are independent, well, this expression here, the probability of B given A, is actually the same as the probability of B. That's what independence means. It means that the conditional probability of B given A is just the same as the probability of B. So if A and B are independent, what we get is this. So we can replace this now just by the probability of B. So this is the normal way that you see independence defined. So let me put a box around this equation here. So we say that two events are independent if the probability of A and B is the probability of A times the probability of B. So this is your definition of independence, or the formal definition of independence. Okay, so what have we done here? Well, we started off with an intuitive idea. The intuitive idea of independence is that the two events don't affect each other. So think about the coin flip and the die roll. Those two things don't affect each other, so we think of them as being independent. So intuitively then that tells us something about conditional probabilities. If A doesn't affect B, then the probability of B given A should be just the same as the probability of B. And then from that we use the multiplication law to get this definition down here, that the probability of A and B is just the probability of A times the probability of B. And this is the kind of standard mathematical definition of independence. Okay, so in probability theory, this is what you mean when you say that two events A and B are independent. It means that the probabilities of A, of B, and of A and B are related by this equation. Okay, so now let's look at some examples. Okay, so our example here involves rolling a fair die, and I've listed three events. So event A is the event of rolling a 6, B is rolling a 5 or a 6, and event C is rolling an even number. Now the question we want to look at here is which pairs of these events are independent, right? So when you're talking about independence, you're talking about a pair of events, and you have to ask whether or not the pair is independent. So what have we got to look at? We've got to look at A and B together. Are they independent? We've got to look at A and C together. Are they independent? And then we look at B and see if they're independent. Now, to understand independence, we're going to have to work out probabilities. So let's work out the probabilities of each of these events first. So the probability of A, well, that one you should just be able to say it straight off. Rolling a 6, given a fair die, the probability is 1 over 6. Okay, you have 6 equally likely outcomes. The successful one is a 6, so there's one successful outcome, so your probability is 1 over 6. What about B? Well, there you've got two successful outcomes, a 5 or a 6, so the probability of B is 2 over 6, which is 1/3. And what about C? The probability of rolling an even number. So now there are three successful outcomes, 2, 4, or 6. So we get a probability of 3 over 6, which is 1/2. So that tells us the probability of each of the individual events. So now what about when we combine them? So to look at independence, we'll have to look at things like A and B. So remember, the way we write AND in probability theory is we put this intersection symbol here, the intersection of event A and B. So what is that? That's the probability of rolling a 6 and rolling a 5 or a 6. Well, how many successful outcomes are there? Well, if we want to roll a 6 and roll a 5 or a 6, there's only one successful way to do that. That's to roll a 6. So the probability of A and B is 1 over 6. What about the probability of A and C? So the probability of rolling a 6 and rolling an even number. Well, again, the only way to do that is to roll a 6. That's the only way to satisfy both conditions of rolling a 6 and rolling an even number. So the probability of A and C is 1 over 6. And the probability of B and C, so again, we want to roll a 5 or a 6 and roll an even number. So again, there's only one way to satisfy both of those conditions, and that's to roll a 6. So there's only one successful outcome, so 1 over 6. So now we have all the numerical information that we need to work out whether or not each pair is independent. So let's look at A and B. So let's look at the pair A, B. Right? Are events A and B independent? So we have. So the question we have to ask is the probability of A and B, is that equal to? So I put a question mark here. Is that equal to the probability of A times the probability of B? Okay. Well, now we have the values of all these things. The probability of A and B is 1/6, and the probability of A is 1/6, and the probability of B is 1/3. Well, so we're asking, is this equation true? And no, it's not. It's false. 1/6 is not equal to 1/6 times 1/3. So those two things are not independent, and that makes sense, right? Clearly, rolling a 6 should not be independent of rolling a 5 or a 6. Okay, so let's look at the other pairs. Let's take the pair AC. So is rolling a 6 independent of rolling an even number? So the probability of A intersection C, is that equal to the probability of A times the probability of C? That's what we have to ask, right? Because that's what would be true if these two events are independent. So the probability of A and C is 1/6, and the probability of A is 1/6, and the probability of C is 1/2. And again, this is false. So rolling a 6 and rolling an even number are not independent. So finally, let's look at B and C. So that's B is rolling a 5 or a 6, and C is rolling an even number. Are they independent? So B, C, right? So the probability of B and C, we have it in our little table up here. It's 1/6. The probability of B, so we're asking, are these two things equal? So on the left hand side we have 1/6. On the right hand side we have the probability of B, which is 1/3, times the probability of C, which is 1/2. And these are equal. So this one, this equation here is true. So that means B and C are independent. So B and C are independent. And that mightn't be immediately obvious if you think of independence purely intuitively, right? B and C, remember, are events concerning the same die roll. So let's go up again and recall what they are. So B is rolling a 5 or a 6, and C is rolling an even number. So you might say, well, you know, they're both something to do with the same die, so they can't be independent. But actually, from the probability theory point of view, these two events are independent. And we just checked it by just verifying that the equation for independence is true. So rolling a 5 or a 6 and rolling an even number are two independent events when it comes to rolling a fair die.